Hi everyone. This is my discrete mathematics midterm for this semester. I would like to give the solutions to this exam, starting with the first question, which is related to proofs, actually. Let's look at the question first. We would like to prove for positive integers and any k up to n that n choose k is equal to n minus 1 choose k minus 1 plus n minus 1 choose k. So in this question, there are two parts. In the first part, we need a combinatorial proof. The left-hand side is the number of ways to choose a group of k elements from a group of n items, this part. The number of ways to choose k items out of n. Find a description of the right-hand side that amounts to the same thing. So combinatorial proofs are typically like this. You want to prove an identity, meaning an equality. So for both sides, the left-hand side and the right-hand side, you come up with a description, such as counting something in a way. And you do that for two different ways. So you describe the same outcome, but through two different procedures. So the outcome should be exactly the same. Therefore, you sort of argue the two sides must be the same because they are counting the same thing. So here, the left-hand side is, well, that's trivially given. And what is asked is a description of the right-hand side that would amount to the same thing. So the left-hand side, n choose k, this here, is obviously the number of ways to choose a group of k elements out of a population of n. So what could be the right-hand side? So I have two components here. You see n minus 1 choose k and n minus 1 choose k minus 1. And in what ways can I interpret this so that that will amount to choosing k items, a group of k out of a population of n? Now, one way to think about this is, well, ultimately I want to choose k items out of n. So consider these n items, 1, 2, dot, 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 let's say n minus 1 and n. Now I want to choose k out of this, so I can do that in one shot, and the number of ways to do that is n choose k. Or alternatively, you can consider the following scenario. Choose arbitrarily one of the items, let's say n. Okay, so put that aside. Okay, it's still a group of n, but I'm going to consider two different, let's say, sorts of groups. In one group, or rather in one sort, I have this element n chosen, and in the other sort, I don't have this. So I can do this in two ways. I can include the number n, the item n in my group of k, or I can exclude item number n in my group of k. So you see this here, n minus 1 choose k minus 1. What's that? That's the number of ways to choose k minus 1, a group of k minus 1, out of n minus 1. So from this group, choose k minus 1 items from this group and add item number n. So this is one way to form a group of k. You can choose k minus 1 out of the first n minus 1 items, and you can add item number n, which in total will give you a group of k. And these groups, each of them will include n. item number n. So now I'm going to put this aside. That's one way. And alternatively, again, from 1 up to n minus 1, and set aside n. Now from this group, choose, here I had chosen k minus 1. Instead, choose k items from this group and exclude this in my group, right? So this is again going to give me a group of k items, but these will not have item number n in them, okay? And therefore these will form in total the number of ways to choose a group of k out of a population of n. You see, the number of ways I can do this is n minus 1, choose k minus 1, because out of n minus 1, I'm choosing k minus 1. So that's this, n minus 1, choose k minus 1. And this right-hand side, that's it. How many ways can I do that? I'm choosing k items out of a population of n minus 1. So that's n minus 1, choose k. So therefore, if I add these two up, I should get n choose k, but because that's the total number of ways to choose k, a group of k, out of a population of n. Therefore, this is my combinatorial proof. You see, on the left-hand side, I have n choose k, which is the number of ways to choose a group of k out of n. And on the right-hand side, I have sort of a two-step procedure. First, I decide whether I want to include n or one of the items in my group at all. If I include it, it will be n minus 1, choose k minus 1 ways to do that. If I exclude it, it will be n minus 1, choose k ways to do that. So if I add them up, it should be n choose k. So that concludes the combinatorial proof. Right, so that's part A. Let's move on to part B. Here we want an inductive proof. Prove the statement using induction. So that's the statement here. K less than or equal to n, and choose k is equal to n minus 1, choose k minus 1, plus n minus 1, choose k. Now here, n is in the set positive integers. So, well, the inductive proof, it needs a basis, and therefore for the base case, I can set n equals 1. Okay, so n equals 1 is going to be my base case. Why? Because it is given in the question that n should be a positive integer, and for any k less than or equal to n, this should hold. So I have to show that this equality holds for k less than or equal to n, means k must be either 0 or 1. So this means the left-hand side, n choose k, is equal to n minus 1, k minus 1, plus n minus 1 choose k. So is this satisfied for this particular scenario? And plug that in. For k equals 0, n equals 1, 1 choose 0, is that equal to 1 minus 1 choose, well, 0 minus 1. This will not be meaningful in this context, since I have a negative number in this expression. I will disregard this. Instead, I'm going to take k equals 1. So I'm just going to erase this, put a 1 here. And for k, I'm going to put another 1. So this is just 1, right? Okay. So the left-hand side is just 1. And the right-hand side is 0, choose 0, and 0, choose 1. Now, in this case, this is 0 because you cannot choose a group of 1 out of nothing. So there are 0 ways to do that. And this one is 1 by convention, because 0 factorial is by definition equals 1. Therefore, this is equal to 1, which means the base case is satisfied. Okay, now I'm going to move on to the inductive case. Now, what is important here is that you have to remember how mathematical induction is formulated. In the inductive case, I have an inductive hypothesis, and based on that, I am going to show an implication is satisfied. So my inductive hypothesis or assumption is going to be Pn, which is, well, precisely this statement here. So I'm going to assume this is going to work. So I'm going to assume this is true. And based on this, I want to show this implication. Okay? What I want to prove is the implication itself. Okay? And what is Pn minus 1? That will be n minus 1 choose k is equal to n plus 1 minus 1 choose k minus 1 plus n plus 1 minus 1 choose. Am I taking that correctly? So this is k minus 1 and this is k. Okay. And therefore, rewriting these, I have n choose k minus 1 plus this is n choose k. Okay, this is the statement. N plus 1 choose k equals n choose k minus 1 plus n choose k. Okay, so the left-hand side is n plus 1 factorial divided by n plus 1 minus k factorial. K factorial is this equal to n factorial, n minus k plus 1 factorial, k minus 1 factorial, plus n factorial, n minus k factorial, k factorial. So you think if I show this, the proof will be done. So what can you do here? You can take the left-hand side or the right-hand side, and you can try to reach the left-hand side. So you see n factorial in both terms here, and in the denominator. So what we can do is, let's say, n factorial parentheses 1 over. Now, I would like to have the denominators equal. So I'm going to manipulate here to make them manipulate this expression to make the denominators the same. So this is n minus k plus 1 factorial, and this is n minus k factorial. And therefore, the one on the right, this one, is missing one term to be equal to this one. So instead of n minus k factorial here, I'm going to multiply this with n minus k plus 1. So it should also go to here. I will have the plus sign in between. So this one makes these two the same. And here you see I have k factorial, and here I have k minus 1 factorial. So I'm going to put the k factorial here and n minus k plus 1 factorial. And instead of k minus 1 factorial. Now, I would like to multiply this with k and also multiply this with k. So the expression doesn't change. And now I can manipulate this. Since the denominators are now the same, I can write this as, let me put equals here. And I'm going to write this in one shot. So it will be n minus k plus 1 factorial here. And this together will be k factorial. And in the numerator, what do I have? So n factorial here. And this k plus what I have here is n minus k plus 1. So this is a little bit too much. Okay. And now you see here I have minus k canceled out with this k. So I have n factorial multiplied with n plus 1 over, what do I have in the denominator? N minus k plus 1 factorial k factorial. So this is, in short, n plus 1 factorial over n minus k plus 1 factorial k factorial. And in short, this is n plus 1 choose k. And that is the left-hand side, I believe, here, this here. And therefore, you would think the proof is done, but you would be wrong. This is not an inductive proof in this form, okay? You need to be careful here. So the algebraic manipulations all check out. Nothing is wrong here, but the argument is insufficient. You are not done yet. There are two things you need to take care of, or there are two ways you can approach this. What I'm trying to prove is this implication, not this by itself. Okay, there are two things you can do, as I said. One thing you can do is, you see, you could argue Pn plus 1 is true no matter what Pn is. So you have shown this is true, which means the implication, something implies true, must be always true, right? Because whether Pn is true or false, the implication, true implies true or false implies true, will always be true. So if you make this argument, I have shown that Pn plus 1 is true, which means the implication is true, therefore the inductive proof is done. This is okay. This is acceptable as an inductive proof, but if you do not state that explicitly, you should say that P of n plus 1 is true, therefore this implication is always true, therefore the inductive proof is done. If you don't argue it like this, if you just show that P of n plus 1 is true by itself, this proof is incomplete. It's not enough, let's say. Okay, so this is one way to argue that the statement is true using induction. But this is sort of a perverted induction, because you just show that P of n plus 1 is true no matter what P of n is. So as I said, unless you explicitly state that the implication is true, and now that the inductive proof is done, your proof will be incomplete. So what I'm going to show is the second way to do this, which is a little bit more convoluted, and typically you wouldn't want to do that, but this is going to be a typical inductive proof. So I'm going to erase all these. Okay, so this part, let's get rid of. And now, what you need to do is assume Pn is true, which means, i.e., n choose k is equal to n minus 1 choose k minus 1 plus n minus 1 choose k. So I'm going to assume this is true. Now, we have shown this using a combinatorial proof in part A, but in this part B, as of yet, I don't know this is true. Okay, remember the characteristics of an inductive proof always. This is my assumption. I'm assuming this is true. And under this assumption, I need to show that this here is true. So I want to show under this assumption that n plus 1 choose k is equal to n choose k minus 1 plus n choose k. Okay, and by the way, this is for all k less than or equal to n. Let's also not forget that. I have to make use of my assumption. That is the heart of this proof. So this, I want to make use of, okay? So starting from the left-hand side, n plus 1 choose k. Now, I cannot apply my assumption here because, well, I only assume this only for n, or if I use strong induction, I only can assume this up to n. So n plus 1 choose k, I cannot assume this. The statement will also hold for this. So I cannot make use of the left-hand side. So I need to turn my side to the right-hand side, this statement. N choose k minus 1 plus n choose k. And now these I can apply the assumption. And well, instead of this, because this will make n to become smaller, but I want n to grow. Instead of this, I'm going to first manipulate the left-hand side, n plus 1 choose k, into n plus 1 factorial, n plus 1 minus k factorial, k factorial. So I'm going to make this look like n choose k. So this will be n plus 1. So here I want n factorial. And in the denominator, I would like, what do I want? To have n choose k. Here I need n minus k factorial and k factorial. So to hold the equality, what do I need? So the numerator is n plus 1 factorial. So that's done. And in the denominator here, I do have k factorial. That's good. But I also need this term here. Well, there's the factorial here. N plus 1 minus k factorial. Instead, I have n minus k factorial. So what do I need here? As an extra term, I want n plus 1 minus k. Okay? So now I can write this as n plus 1 over n plus 1 minus k times n choose k. Now, to n choose k, I can apply my assumption. To this one, I cannot apply the assumption because you see n minus 1 is not less than or equal to n. But this one, I can write as n minus 1 choose k minus 1 plus n minus 1 choose k. Okay, so this is the assumption applied. Now this does look like I'm using my assumption to show the implication. And then the rest is algebra. I'm going to manipulate all these terms. And what do I want to get? I want to get this statement here. Right. So what do I have here? N minus 1, choose K minus 1. N minus 1, choose K. And what do I want? N choose K minus 1. And here I need N choose K. So let's write this as N plus 1 minus K, N plus 1. So here I need N minus 1 factorial. N minus 1 minus K minus 1 will give me N minus K factorial and K minus 1 factorial plus, can I fit it here? So maybe I should pull everything to left a little bit. Okay, so that's N minus 1 factorial divided by N minus 1 minus K factorial, K factorial. Okay, so from this, I would like to reach to these two terms, this one and this one. And inspecting what I have, so I have N minus 1 factorial in the numerators, so I would like n's. So let me put this here, N plus 1 minus K, and both of them, I would like a multiplier of N. So let me divide this by N and make this N factorial, also this N factorial, because that's what I want in both of the terms. And then in the denominator, what do I need? For the first one, this, I want N minus K plus 1. Instead, what do I have? I have N minus K. So here, if I want N minus 1 plus K, is that what I want? No, I want N minus K minus 1. So that is N minus K plus 1. So I want N minus K plus 1. What I do have is N minus K. So I need an extra term of N minus K plus 1. So I need to put that here, N minus K plus 1. And that's K minus 1 factorial. Is that what I also want? Yes, K minus 1 appears here. So that's good. And for the second one, what do I need? In the denominator, I need N minus K. And what do I have here? Okay, so I need to separate them because the multipliers here are different. So I'm going to keep this as a 1 and move these a little bit. Okay. And now here, this is N minus K plus 1 times this. And the one on the right, I want N minus K factorial here. And N minus K will be here because this is up to N minus 1 minus K. And I have the K factorial term here. Now I need to combine these two components into the required expression. I need some space here. So actually what I'm going to do is I will delete some of these intermediate steps. Also this one I'll get rid of. And let's move this somewhere here. So I'm going to move this a little bit. Okay, I don't need the equal sign. So this is what I have at the moment. And let's remember what I'm trying to reach. Um, this is my statement, but I need for n plus 1. Therefore, here I need n choose k minus 1. And for this one, I need n choose k. And this term you see here is actually going to give me n choose k minus 1. So that will be the first term. You know what? I can directly actually write here n choose k minus 1. And let me also move these. Get rid of this. And here, well, yeah, this will be n choose k. And that will be with a factor of n minus k. So this is what I have. And I just want these two, actually. So hopefully, after algebraic manipulations, I'm going to end up with only those two. So let's look at this expression one by one. So if I take this out, take this expression out, this and this will cancel out. Therefore, I will be left with n plus 1 over n times n choose k minus 1. And this will be, so in the numerator, so I'm going to completely take this one and multiply with this one. So in the numerator, I will have n plus 1 times n minus k divided by n plus 1 minus k times n choose k. Okay, now here you see this could be written as n plus 1 over n. Instead of that, I can write this as 1 plus 1 over n. So I can actually set aside one of the terms I need. And then this part here, this will be 1 over n times this plus this remainder thing. So out of this, I would like to obtain n choose k. So this entire thing, I'm going to copy here. Put it here. Again, I'm a little bit short of space. Let me resize it a little bit and put it here. Okay. So hopefully these two together is going to give me n choose k. We're talking about this part. And if I expand it, this here, 1 over n times n factorial over n minus k plus 1 factorial, k minus 1 factorial, plus the other term. Let me forget about that for a minute. And this here, well, I want it to become n choose k. So what can I do about that? So n, here I have n, so that's what I already want. Here I want n minus k, so I can write this as instead of this, I can write this as n minus k plus 1 factorial. So n minus k plus 1 times n minus k factorial. And this k minus 1 factorial is going to become k minus 1 factorial times k, and let me put that k also here. Okay, so you see now, if I take this out, this entire thing here is going to become n choose k, like so. And therefore, I'm going to replace all these with, so this will be k over n times n minus k plus 1 times n choose k. So I'm going to erase all these. And instead, I'm going to put this here. N minus k plus 1, k here, and n choose k, plus this final term here. So in fact, I'm going to put that in n choose k parentheses like so. So I'm going to move this here. So I'm going to put n choose k here, big parentheses. Okay. Plus this coefficient here. Copy this, put it here. Okay, so my hope is this thing here will add up to 1. So that's what I'm hoping for. And I can actually do that here. So let's look at the denominators. The denominators are the same, n times n minus k plus 1. And therefore, I will have in the numerator k plus, so if this turns out to be 1, I will be done. N plus 1 times n minus k. So I'm going to expand it, n squared minus n times k plus n minus k. Okay, so k with minus k goes out. So what I'm left with is n squared minus nk plus n. If I make it into an n parentheses, I will have n minus k plus 1 divided by n minus k plus 1, which is exactly equal to 1. So this thing is indeed 1, and therefore this thing here is indeed equal to this. So now this completes the inductive proof. And under this assumption, do not forget this. You are trying to prove this implication. Okay? Not only this one. If you just prove that and leave it at like that, that will be a direct proof. Okay? If you want to do an inductive proof, you need to use the assumption. The assumption is given here. You need to work it into your derivation so that the inductive proof works. Otherwise, it's a direct proof. It is not wrong, but it is not asked. It is not what is asked in this question. Okay, so that concludes question number 1.